Hi everyone, this is Brett Sanders, and in this video I'm going to provide guidance and instruction on using the seepage functionality of PRIMo. I'm working here with the basic test case that comes with the installation of PRIMo. It's the Miami Gate problem, and you'll notice as you scroll through the input file that one of the lines has an option to sort of load a seepage file and model seepage. And what that will allow you to do is basically represent the infiltration of water into the ground as a function of the imperviousness of the land surface, an infiltration capacity, and a sort of both from a rate perspective and the volume of water that can infiltrate. And then we'll also have a seepage functionality which can transfer that water that infiltrates into the ground into a nearby drainage canal as a shallow sort of groundwater flow through the land surface. So areas like Miami have highly permeable rock underneath the ground, limestones, and water can move pretty quickly through those areas, so it's possible for water to go into the ground and quickly flow horizontally into nearby drainage canals. So we wanted a model that is able to capture that functionality, and we've added that into PRIMo. If you'd like more information about how exactly that's done, there is a research paper that's under development right now to describe that. So for the moment, let's just remind ourselves that we're working in the working on the PRIMo Miami Gate test case. So if we ran PRIMo prep, we would see this is our study domain. We're going to model a case where there's rainfall on this DEM, where there's walls all around all sides, so nothing flows in or out through the boundary. But now we're going to allow water that infiltrates into the ground here to flow to the nearest water body and then start filling in these canals. So the seepage functionality of PRIMo is linked to a land cover classification. And going back to this PRIMo prep, we have this land cover classification, and you'll notice that there is a class that's assigned to all the canals. And what we'd like to be able to do is route any water that infiltrates in these areas to the nearest canal as a way of getting, representing this sort of flow pathway, which may be important in some applications. So note that the land cover classification has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different classes. And as was shown in a previous video, information about those classes can be found in this land cover file. So 1 is the channel, as I just mentioned. 2 is a road, classified as a road. 3 a beach, and so on. That's just an example. So when we now want to configure seepage, what we're going to do is we're going to go and open this seepage file and see the way it's set up. Okay. The seepage file is set up with a series of options for different parameters that are needed by the PRIMo model. So the parameters are a seepage capacity, which is a height. It's like, think of it as the depth to groundwater. So if it starts raining, how much capacity is there before all that space for soil moisture has been used up? The second parameter is an infiltration capacity. So that's the rate at which water can move downwards from the land surface at capacity, when there is capacity. There's an effective hydraulic conductivity, which is a measure of how quickly the water can move horizontally through the ground to a nearby water body. There's a storativity parameter, which characterizes the time rate of change of storage in the system. And there is an imperviousness, which is a land surface imperviousness option. So each of these options can be either a constant, in which case you can specify the constant here, or you can flag this, say, to a 1, and then it will open a file that has to be prepared in PRIMo prep. So in the basic PRIMo prep file is set up with an example of how to generate those files. But you would need additional data from a site, data on the depth of groundwater or the infiltration rates or the hydraulic conductivities in order to be able to use this fully and understand uncertainties and so forth. So there's one other option here, which is with the imperviousness, you have the option of either specifying a constant or inputting imperviousness from a separate file, or specifying it based on land use. And you'll go back here and remember that when you built this table for different land cover classes, you could assign imperviousness this way. So that's another way to get the data in. So what we're going to do in this particular test case is we're going to use constants for all these numbers, and we're going to make imperviousness a function of land use as specified here. And that way we don't actually need to load any of these additional files. So these additional files aren't needed for this particular test case. One additional aspect of this input file is that the model's designed to support the routing of flows from land surfaces to nearby water bodies. And so in this list are two different land covers that qualify as water bodies for the purpose of this modeling. So we can go back to the land cover. Notice that both 1 and 4 are places that water can be routed, and that's either a channel or a natural sort of ocean type land cover classification. So with that in mind, I'm going to go ahead and run a simulation first for you. Actually, it's already been run, but just visualize the results of the baseline simulation. This is rainfall on the ground with the basic runoff, no seepage functionality. This is just the baseline simulation that has been presented in the very first PRIMo tutorial. Okay, but if we want to now rerun this model with the seepage functionality turned on, we turn this flag to 1, make sure all these files have been saved, and now we can rerun the PRIMo simulation. And what we should see when we look at these results is we should see less water on the ground surface and more accumulation of water in these canals based on that seepage functionality that we just input. So certainly we should see more water in the canals because we're already using a runoff coefficient to take some of that rainwater and turn it into infiltration. But we should see more accumulation of water in the canals and in this lake because of that routing that's going on inside of PRIMo. So we've done that now. Let's give it a whirl, press the PRIMo viz and see how it comes together. Yeah, so what you're noticing here is that there's just a little bit more accumulation of water in the canals and in this central lake here because that seepage was turned on. And a lot of that will also depend on the rates that you use for infiltration and seepage. So if we go into the seepage functionality and we increase the infiltration capacity, so that means infiltration can happen at a faster rate. We increase the hydraulic conductivity, so now water is able to move faster through the land surface, or underground surface, and into those canals, and we can rerun the model. These rates are specified in centimeters per second, so some of these numbers might, are on the high side, but Miami's known for having pretty highly porous and transmissive subsurface geology. So PRIMo's running along, and as soon as it's done, we can run the latest, visualize the results. Okay, that's done. We'll visualize the results. think you'll notice that this time we did get a little bit into these brighter blue colors in the canal in here with that seepage functionality, increased a bit. And this is only a simulation for an hour or so. It can take a long time for sort of these seepage processes to respond relative to some of these overland flow processes. But hopefully this gives you an idea of how PRIMo scales the seepage with these different parameters, and how the PRIMo model seepage functionality is linked to the land cover classification. So the idea is that you tell it which of these land covers are places where water can be routed to, and then PRIMo will take water from all the other land covers and move it into those land cover classes that are targeted for infiltration water. Typically open water bodies is what you want to target.